welcome to today's lecture. So far, in this class, we've discussed a number of topics pertinent to life. We've talked about stress. We've talked about fatigue. We've talked about bending. We've talked about failure. But this, today, marks a monumental day in machine design. Because all of these are behind us. We've been broken. We've been fatigued. We've been stressed. We've experienced failure. We've bent. And we've also calculated deformations. But now, I've tested your endurance limit. We've talked about yielding. But you have shown strength. And now we get to discuss freedom. That's right. Today's class is not about all these gross words. It's about this fun word, which we all know involves toting guns around, shouting things, and having an American flag hanging out of the back of your pickup truck. That's what freedom is. Tune in for my next lecture for more life-altering moments. So far in this class, we've discussed a lot of really dark terms. Most of this has to do with failure mechanisms. Okay? And so far in this course, we really have been focused on how to prevent failure, or really how to analyze a component to see if failure is going to occur. The whole reason why you calculate the factor of safety is because if the factor of safety is above 1, it means that your stresses are greater than your strength, which means your component is either going to yield or break or fail. Something's going to happen, something bad. So as we discuss failure and as we talk about all those principles, we really haven't talked about the design aspect of this. A failure is a massive, critical experience that goes along with machine design. You cannot allow failure to occur. If you do allow failure to occur, well, somebody's going to get hurt. Something is going to get destroyed. And, well, you're going to drop out of school. Probably going to end up living in a van down by the river. So, hold on, I was going somewhere with that. Wait, no, I wasn't. When we really get into this, at this point in our class, we're going to start talking about the actual design principles. Now, I'm going to be using a lot of this class to discuss design for components, design for selecting components. A lot of what's left of Shigley's textbook, if you bear with me for a second here. I love this textbook because it has so much in it. But the beginning of this textbook is all about failure. And we go through the first, 6 chapters? Calculating stresses, calculating deformations, calculating fatigue, calculating static failure. And then you get to 7, and things change a little bit. First of all, 7 is part 3 of your textbook. But part 3 of your textbook, all that this is is how to select mechanical components. Each one of these chapters, which comprises more than half the book, each one of these chapters gets further and further in detail about how to pick a shaft, how to design a shaft, shaft components, all of these things. Most of those components have standards and codes and regulatory bodies that exist to define them. And really, for you as a designer, you're probably not going to be sitting down and fundamentally recognizing what is a spring. You're going to go find, okay, how do I pick the right spring and apply it into my system? For the remainder of this course, we're going to be discussing selection of those components. You have to understand failure in order to pick components for any design. You have to. What we're going to be talking about today is the actual design principles needed for moving components. Everything we've done so far has been static. It has been no accelerations, no movements. What happens when now you have some movement in a system? Most machines move. So how do you handle that? Well, it turns out, let me see if I can find a better marker. Turns out that we have extensive documentation on how to calculate moving components. This subset of this course is actually called Machine Kinematics. Basically what that means is, it's for a machine and it's the study of its motion. So really that's what we're going to be talking about. Yes, that was a Chris Farley reference, Hayden. What we're going to be talking about this week is going to be how do you handle machine kinematics. So the first principles that I want to bring up, oh man, that was a terrible marker. The first principles that I want to bring up is, what is a link? Okay, a link is a playable character that chases the princess and fights the pig. Okay. Depending on what iteration you're looking at, there's a whole lot of yeah involved. Yeah. Well, I'm teaching you culture. I don't get nearly enough thanks for this. Pearls before swine, or master swords before swine. I don't know. Basically, what a link is it is a power transmitting component. Okay, that's it. Power transmission. Well, remember, power, if you remember that from Physics 1, we talked about power and electronics. What power is power is the derivative of energy, which means we're now looking at components that have energy, aka moving. They have energy in the forms of kinetic energy. They have energy in the forms of potential energy. And this potential energy is oftentimes derived from the stresses and strains that it experiences. Your stress multiplied by your strain is equal to the elemental energy that's contained inside of a small piece of material. Okay? That's the whole principle of the DET, deformation energy theorem, with von Mises stress. The idea is that it's storing energy in the forms of deformation. as you transfer power, you will always have a collection of these two. And it does also involve some heat because they are moving components. But as this is now a kinetic component, what we can now look at is that power, the formula for power for a linear system is force times velocity. It's actually a cross product. Okay? The cross product of force and velocity is equal to the amount of power that's being transformed. If you know how much power is being carried through a component, or if you know how much power is being put into a system, all of that power has to be accounted for. If you are using a 3 horsepower engine, with each horsepower equaling roughly 740 watts, that's 3 times 740 watts of power you're plugging into your system. If your vehicle motor is a 400 horsepower motor, which, yes, I drool over that because I don't know what I have in my car, but I got it because it had a lot of power. I'm not going to pull that out on YouTube all of a sudden. I thought I knew it off the top of my head, and I didn't. You're chugging a lot of power through your system. Okay? Now you're looking at how much force are you able to apply per how much velocity. At really low velocities, your forces are very high. At very high velocities, your forces are very low. If your system is operating at a very slow speed, but is transferring a lot of power, you are exerting a significant amount of force through that. Okay? This is for a linear system. So the power exerted by your vehicle ultimately comes out in the form of power, in the form of how much force is exerted by your tires on the pavement, times the velocity of your vehicle. Okay? Or we can talk about rotational. It's torque times angular velocity. Again, a cross product. Okay? You want to also talk about power? It's current times voltage. For an electric vehicle that's producing a significant amount of current and producing power out of it, how much current is it consuming over how much voltage is that motor? That's how much power it's consuming. Okay? And you can talk about heat transfer energy. How much power is being given off to the environment? Okay? When it comes to power in a system, you're looking at generally these 4 systems. You may also be looking at hydraulic, pneumatic systems. This is 350 stuff. Power has to come from somewhere and go to somewhere. And it goes through links to do that. So this is ultimately what a link is. It's just a power transmission member. It's not an active component. It's not something that actually creates power. It's not something that dissipates power. It's just a transmission piece. That's it. And you're designing for how can we handle how much force is being exerted through this component based on how fast it's going, based on how fast it's spinning. These two are usually the types of linkages that we're talking about. But do be aware that these exist too. A hydraulic and a pneumatic cylinder, through use of pressure, are going to exert a significant amount of force on components. That's how it works. So in machine design, we cover these two when we try to cover these two. I had a question in class this last week. Who's going to tell you how much force is being exerted on a component? Well, quite frankly, it comes down to the system that you have. A mechanical system is comprised of the following components. You have actuators. Sometimes multiple, sometimes you only have one. From that actuator, power is input into the system. This can be a motor. This can be a piston cylinder. If you want to look at it, its base root. A piston cylinder actually uses pneumatic power generation through a chemical process to produce an exorbitant amount of pressure inside of a piston head. Well, inside of a piston cylinder that gets pushed on the piston head, ultimately gets transferred through the camshafts. Okay? This actuator is a power generating, assumed, because even then it's not really power generating. The power for an electric motor ultimately comes from a battery or comes from a power grid. I mean, we're just transferring power. If you really want to trace everything back, most of the power we have comes from the sun and at its root. And where did the sun get its power from? Well, that becomes more of a philosophical discussion or a theological discussion. We'll sit here and talk about God here in machine design. But at its root, in a mechanical system, we're going to assume that this is a power generating member. We're not going to look at the before times. Although if you want a rousing theological discussion, hit me up after class. Okay. From the power generating elements, it travels through linkages, which is just a sequence of links. What these links do is it changes the power. Okay? It may change the power by reducing, transforming the force, converting force and torque, converting it between these power mechanisms, may reduce velocity, may limit torque. You have some elements that exist that mitigate. You can have linkages that serve as control systems. A suspension in a vehicle is a control system itself, where your actuator is actually the roadway pushing up on the tire. Your linkages are your springs, they are your dampers, they're your tire, they're your axle, all of those components that transform the actuation, which is where the power is coming from, and convert it into some kind of an output. Okay? So this is your mechanical system. You're trying to perform some action given some actuator, and you're designing all of your components in between to make sure that the power that is transmitted through them is not substantial enough that it causes it to fail. One thing that I mentioned at the end of class last week was you have a number of design variables available to you. Yes. The sun gets power from Bang Energy. This is where I get my endorsement deal, right? For energy drinks. Hold on, I'm going to change out my battery real quick. So I will go. We'll go dark for a second, but I'm about to tell you all the principles of life and everything you need to know. You should make. So make sure to do that. Now we'll get back to class. So, in a mechanical system, what we're talking about specifically in this class is linkages. Okay, we'll talk about selection of actuators. We can talk about outputs, but this is really where the meat of everything comes from. Okay, what we're doing here is we're transforming power. Power comes in. Power comes out. And we make sure that when the power comes in and the power comes out, that power is not coming out in the form of destruction. Unless you're creating like a road destruction machine or something. I don't know. It's your life. So, I'm also going to define the term joints. No, this is not a weed reference. Okay? Forget about it. This is, the term joints is any connection between linkages. Or actuators. Okay? And there's a number of different types of joints. Your reading assignment for this week is you have to look at a number of different types of joints. It's in a paper. I put that on the interwebs. By the way, I also posted a quiz this morning. Yes, you have 2 quizzes due this week. Yes, that's a lot of work, and yes, I only gave you 3 problems for your homework assignment this week again, because I am trying to cut down on work. I told you to forget about it, Tyler! Shh. Someday I'm gonna get sued. Oh well, that's life. So, when we're talking about joints, you can have anything from a revolute joint, which, if we have a linkage here, that where, let's say we have a piston, and your piston is pushing in and out like this. Maybe this has a linkage on it. It connects just with a simple bolt connection. Bolt connection is called a revolute joint. A simple revolute joint, it doesn't carry torque. It allows for movement in multiple directions and rotation around the system, but it does not allow for movement in this direction or this direction. I cannot grab this link and pull it this way without also having to move my piston. I cannot grab this link and move it this way without also having to either rotate my piston or break my piston. Okay, that joint prevents X and Y movement, but it allows for movement about the Z-axis. Okay, I can rotate about the Z-axis all day. That doesn't hurt anything. Okay, similarly down here, another revolute joint. It allows for rotation about, so this restricts movement in the X and Y direction. It also restricts rotation about the X and Y axis. When you have something bolted, you try to twist it, you're pushing on the bolt. It doesn't allow that to happen. Well, at least a properly bolted connection. If this is a really loose bolted revolute joint, yes, you do have a little bit of play in the R, Y, and RX direction. But it restricts these, and it allows movement in the RZ. And depending on how you design it, if it's just a tube or a cotter pin that goes through there, it may even allow movement in the Z direction. What a lot of times what we'll do is we'll say, let's just focus on planar kinematics. Planar kinematics are a little easier to work with. In planar kinematics, we cut out RY and RX, and we cut out Z movement. And we only focus on X, Y, and RZ. That's planar. Okay? Rotation in the Z direction, movement in the X and Y direction. So if we're only talking about planar movements, we're going to be discussing these. If we're talking about gross movements, we'll discuss all 6 axes of movement. So this brings up an interesting point. If I have, let's say I have a bar right here, and I'm going to mount it directly to the ground with a revolute joint. I'm going to bolt it to an anchor on the ground. Okay? And here's my bar. Bar goes up. I'm going to bolt it to another bar right here. And then I'm going to bolt that bar to another bar that comes down here and also is mounted to the ground. Does this move? Can I move this system? Well, the answer to that is actually yes. This does have some movement in it. How do you find the movement of this system? How do you define the movement of this system? Okay, we have a number of revolute joints here, and all these revolute joints connect these pieces together, but how do we know this system is going to move? Okay, if you have a system like this, where it's mounted again to the floor, is this one going to move? If I were to attach an actuator to this, say we get our piston cylinder, we hook it up, and we connect it right here, am I going to be able to force this system to move? Let's say I do the same thing over here. Hook up a piston, connect it right here, revolute joint, and I try to power this using a piston. Is this system going to move? Well, I can transform the movement of this system based on how I set up my linkages. This is actually called a 4-bar linkage system. This system will not move at all. What's the difference between the two? Well, this is what we end up discussing. It's called degrees of freedom. Okay, mentioned that term at the very beginning. Degrees of freedom is kind of a complex term. Basically, this says how many independent motions do we have in a system? Okay, and this is the idea of degrees of freedom. In my finger alone, let's say I'm just going to fix this joint right here. Okay, in my finger alone, I can rotate my finger here. I can rotate this joint of my finger. I have rotation about 3 joints right here. Okay, but I can also wiggle a little bit in this direction. Okay, this is no. I have multiple ways that I can move my finger. I can spin it in a circle. Okay? I even have a little bit of give if I want to twist it. I have a significant amount of degrees of freedom just in my finger. If I now want to go look at my arm, all the way from my shoulder to my finger, I now have the degrees of freedom that come from just my finger, but I now have the degrees of freedom that come from my elbow. I can twist it, I can rotate it this way. Twisting actually happens primarily at your wrist, not your bones here don't move when you rotate. These bones do. You can flex it. I mean, there's a significant number of independent motions that I can have. I can configure my hand to put my finger in the same place. And I can configure my finger in the same place, and without moving my shoulder, I can configure my arm in multiple different locations. That's a number of different independent systems that allow for the exact same output movement. The human body, and really most bodies, have too many degrees of freedom. And robotic systems are given about 6 degrees of freedom. They have those degrees of freedom when we discussed. That's about it. That's what they're designed to handle. They do not have the ability to have the kinds of dexterity that we do, because that's not how they're designed. And it would require so many actuators, it would make them ridiculous. It's one reason why robotic motions are so weird, is because they don't have the same degrees of freedom that we do. Even the way that I hold my hands like this is a form of expression, because I can hold my hands like this, it means something else. Hold my hands like this, forget about it. It means something different. It is different entirely. The way that I transmit power through my linkages, my arm, my bones. And your body, your bones are your linkages. Your joints are your joints. Your actuators are your muscles. And you have a butt ton of actuators. Okay? So when it comes to independent motions, let's not talk about biomechanics. Let's talk about systems, machine systems, mechanical systems, because those are a lot easier than biomechanics. So when we're talking about degrees of freedom, we have degrees of freedom. There's really two branches of degrees of freedom to talk about. Okay, there's planar degrees of freedom, and then there's three-dimensional degrees of freedom. And an analysis in both of these types may yield different results. It's two different ways of looking at the same thing. It's kind of interesting. In a planar system, you'll have X, Y, and RZ movement. In a 3D system, you'll have X, Y, Z, RX, RY, RZ movements that you have to account for. Okay? The ball joint in my arm is not a planar system. In a planar system, you can take a piece of paper, lay it on top of it, and that paper will never get cut. I can't lay a piece of paper on my arm and do this without slicing right through the paper, because this is a three-dimensional motion. There's nothing planar about just my shoulder joint. Ball joints are inherently three-dimensional, whereas revolute joints, two-dimensional. Slider joints, two-dimensional. Okay? You can have slider joints that are three-dimensional, but they're whack, and it's pretty awesome. So when we're talking about degrees of freedom, first of all, we need to know about whether or not the system is going to be planar or 3D. Planar systems are substantially easier to design. 3D systems require a whole lot of constraints. Okay? Every joint has a number of degrees of freedom associated with it. Okay? Joints have degrees of freedom. Okay? I'm going to have to do a follow-up lecture on this because I ran out of time on what I expected to be able to cover in this class. I got really excited using a New York accent. We're going to go ahead and jump to the next lecture on 4-bar linkages and cams, and we'll get back to degrees of freedom at a lecture later this week. So I'll see you then.